Hey ladies, so today we're working on section 6.3, which we're actually proving identities today. So before in section 6.2, we did a lot of verifying in section 6.1, 6.2, so there's a lot of verifying. So we did it by graphing, and we also did it by proving it for a specific point. So just remember that verifying and proving are not the same thing. So by verifying, you're only doing by specific cases, or I guess for the graphing, it's not absolute, it's not certain. So this is not how you prove an identity. That's just verifying it. To actually prove it, we were going to go through a couple guidelines, and we're actually going to compare how to prove and compare that to solving. So to prove an identity is true for all permissible values. That's the key word there, is all permissible values. We need to express the identity in equivalent forms. So one or both sides of the identity must be algebraically manipulated. So let's repeat that. So one or both sides of the identity must be algebraically manipulated into an equivalent form to match the other side. So there is a major difference between solving a trigonometric equation and proving it. So it's going to go along the same lines as verifying versus proving. So when the first part here, so when we're solving a trigonometric equation, that determines the value that makes a particular case true. If it'll right there we go. So you perform equivalent operations on both sides of the equation. So that's also another little key point. So on both sides of the equation, or in other words, you perform operations across the equal signs. So what you do to one side, you do to the other. And to do that, you then isolate the variable and solve. So the second part here, so this is comparing to proving an identity. That shows that the expressions on each side of the equal sign are equivalent for all values. So that one there we've kind of talked about already. So it's equivalent for all values for which the variable is defined. Therefore, you work on each side of the identity independently, and you do not perform operations across the equal sign. So that is really key. If you do something to one side, it should not be done onto the other side, so you'll have to do equivalent forms. So make sure you do not do the same thing. What you do to one side, you do to the other. That is not applicable in this point. We'll see some examples of what I'm talking about here, okay? So just quickly, we'll talk about some tips for proving identities. It is easier to simplify a complicated expression than to make a simple expression more complicated. So start with that more complicated side first. Our second tip there is to use known identities to make substitutions. So that's going to be going back to our little cheat sheet here, if you guys don't mind me flipping over to our little trigonometric identities. So try and use these, reciprocal identities, quotient identities. Try and make it look into these forms rather than something super complicated. So if you were given, say, something like, let's do this one. What if you were given sine squared of theta? If you needed to, maybe you could rewrite that as 1 minus cosine squared theta. We'll see some examples, so this might not be making sense right now, but we'll look at some examples, okay? So let's go back to our notes there. Alright, so use known identities to make substitutions. Do not go with crazy ones, especially even when we're dealing with the double angle identities. If we're dealing with really crazy angles, don't use those crazy angles. Use the ones that you know and you can work with, okay? So your third one is, your third tip, if a quadratic is present, consider the Pythagorean identity first. It or one of its alternative forms can usually be used. So there's a big key there if when we're dealing with, if this will go away or not, okay. So when we're dealing with a quadratic, use Pythagorean identities. That's when you're dealing with examples like sine squared of theta, or say tan squared of theta. When you're dealing with this, you can rewrite them using those Pythagorean identities to make them look similar to, say, whatever's on your right side. So your fourth tip there is to rewrite the expression using only sine and cosine. Those ones are typically the easiest to work with. So if you can, try and keep it in those terms. Most of it obviously simplifies to maybe something nice like tan or cotan. But typically try and use sine and cosine. They're really nice values to work with. And they do not have any non-permissible values unless if they're in the denominator, so it's always good to use sine and cosine. They're really nice ones to work with, so we'll try and keep it that way. And your last tip there is to factor to simplify expressions. If, say you have sine squared minus 1, you could factor that to be sine minus 1, sine plus 1. Those are some examples. We'll look at one later on, but you guys have kind of already seen this through different units anyways, so hopefully you'll be alright, but we'll look at some examples though, so don't worry. Alright, so for our first example here, we need to first of all verify numerically that 1 minus cosine squared is equal to sine of x times cos of x times tan of x for some values of x. And here we need to work in degrees, and then we're going to take that exact same equation and we're actually going to prove it, okay? So first of all, let's just get some practice in. Let's find those non-permissible values here. So to look at those non-permissible values, you look first of all at your left-hand side. You have to ask yourself, does cosine of x, does that one have any non-permissible values? No. And there's also no fraction in that one, so that is amazingly nice, so we don't have to worry about any non-permissible values on your left-hand side. On your right-hand side, you go through each function. Will sine of x have any non-permissible values? No. How about cos of x? No for that one too. But then we get to tan of x. So tan of x, that one can be written as a fraction. So we have sine of x divided by cosine of x. So then you have to ask yourself, what values would make that undefined? So what we really want to know is, when will cosine of x equal 0? Okay, and then at that point, that is where you will have non-permissible values. So at what values is cosine of x equal to 0? Using your unit circle, or if you guys know that off by heart, you should know that that is 90 degrees and 270 degrees going on. And then you guys can do, you don't give us a restriction, so we can do it for a general solution there. So what we can say is that x cannot equal 90 degrees plus 180 degrees, if you guys take that difference here. And that'll be multiplied by some value n, where n is an element of integers. Hopefully by now we have lots of practice with that. So your non-permissible values for that one is 90 degrees plus 180 degrees, n, where n is an element of integers. So now what we can do is, now we've had some practice looking at some non-permissible values. Now let's verify one. So big thing here is, let's not pick a value that is non-permissible. So let's pick a different one. And it doesn't matter which one, assuming that if this is an actual identity, no matter what you pick other than your non-permissible values, you should find that it is true. So for example, let's pick 45 degrees, just off the top of my head, okay? And you're going to substitute in 45 degrees where every time you see x. So here we have 1 minus cosine squared of 45 degrees is equal to the sine of 45 degrees times the cosine of 45 degrees times the tan of 45 degrees. Okay, and then from there you simply just solve. So you have 1 subtract cosine squared of 45. You can look at what is cosine of 45. That is root 2 over 2, and that's all squared. And that is equal to the sine of 45, which is root 2 over 2. Times that by the cosine of 45, which is root 2 over 2. Times that by the tan of 45, and that one is just 1. Okay, so from there you guys can just solve. I'm just going to draw this all the way up here. Okay, so here we have 1 subtract, and if you guys do root 2 over 2 squared, be root 2 over 2 times root 2 over 2. That is equal to, then we can simplify here, so we have root 2 times root 2, which will be 2. That is divided by 2 times 2, which is 4. Then we can simplify the left-hand side, so we can go 1 minus root 2 over times root 2 is 2, and 2 times 2 is 4. That is equal to 2 over 4. And we can, if you guys want to, we can rewrite that as 4 over 4. Subtract 2 over 4 is equal to 2 over 4. Lots of 4s. And simplifying here, we get 2 over 4 is equal to 2 over 4. So that works. So right there we just verified numerically that 45 degrees is a value of x. So now what we're going to do is we're going to prove that 1 minus cosine squared of x is actually equal to sine of x times cosine of x times tan of x. So here we just verified for 1 point, say 45 degrees, that it works for that value. So now what we're going to do is we're actually going to prove that this whole identity is actually an identity, okay? So make sure you guys pause this. I'm going to erase this so I can continue writing on this, I guess, Word document. Hopefully you guys still have some room there. If not, you guys can write on some paper. But so pause it right now. I'm going to erase all this stuff here. Alright, so now what we're going to do here is we're going to prove that 1 minus cosine squared of x is equal to sine of x times cosine of x times tan of x. So there's 3 options that we can do when we're trying to prove that two sides are an identity. So the first way that we can do this is we can just examine just the left-hand side of our equation. So we can manipulate 1 minus cosine squared of x to look like sine of x times cosine of x times tan of x. Another option you guys can do is just manipulate just the right-hand side. So let's make sine of x times cosine of x times tan of x look like 1 minus cosine squared of x. Or our last option is we can manipulate both individual or independently of one another to look like either or some form of each side. So just remember, you cannot do any sort of identities across an equation, so each side has to be done independently, okay? So because that was a little bit of a rough explanation of how to solve manipulating both sides, that's exactly what we're going to do here. So to start off, we're going to look at our right-hand side there, so that is 1 minus cosine squared of x, and we're going to be using our identities to manipulate that in some sort of way to make our left side look like our right side, okay? So let's look at our identity sheet. I'm just going to quickly flip on over to that. And looking through all of these here, automatically we see this cosine squared theta plus sine squared theta is equal to 1. The biggest thing that we notice is that there's cosine squared theta, and there's also a 1. So the only thing that we're missing there is sine squared of theta. And if we manipulate this equation, we can actually make it look like that left-hand side. And here I'll quickly show you guys how to do that. So I'm just going to write this over here. So here we have cosine squared of theta plus sine of theta, or sine squared of theta is equal to 1. Let's subtract cosine of squared theta from both sides. What we find is that sine squared of theta is equal to 1 minus cosine squared of theta. Now if we actually look at our equation, or that equation that we were given in the question, this 1 minus cosine squared of theta, that is absolutely what we're given on that left-hand side, except we're in terms of x, not theta. So what we're going to do is we're going to rewrite 1 minus cosine squared theta, and that we're going to write that as sine squared of theta. Okay, so I'm going to quickly switch on over to our other document. Alright, so here I'm going to rewrite 1 minus cosine squared of theta as sine squared of x. Or sorry, I guess we're in terms of x here. Okay, so here I simply just manipulated that identity, and it can be rewritten as sine squared of x, which looks a whole lot nicer than 1 minus cosine squared of x. Okay, so for our right-hand side, you guys could choose not to manipulate it, but in this case, let's go ahead and do that. So here we have sine of x times cosine of x, and I'm going to rewrite tan of x. And if you guys remember what tan of x is equal to, that one there is a quotient identity, and that is sine of x, divide that by cosine of x. Okay, so now if you want to, we could keep going with, or I don't know if there's really possible to keep going with our left-hand side. That one, I'm going to say it looks pretty good, so let's just leave it as it is for now. And what we're going to do is we're going to manipulate this right-hand side. So what you notice here is that we have sine times cosine of x times sine of x divided by cosine of x. And your cosines there will cancel, or it'll create just 1. So here we'll have sine times sine, and that is just simply we can rewrite as sine squared of x. So there is that's an example there. So we didn't do anything over the equation sign. What we did to one side we didn't do to the other. We just wrote equivalent form. So we didn't do anything over the equation sign, and we just independently manipulated them to look like one another. So there's one example. So I'm going to switch on over to video number 2, and we're going to finish 2, 3, and 4, okay?